Good afternoon, everybody. And first, let me thank really the organizers, and particularly Jung Hyuk. She really went out of her way and for this wonderful opportunity. Second, I must apologize for those people who heard me in Kyoto. That no, I won't repeat the whole thing, but parts of it. And third thing, there was the references are on a sheet, so whoever didn't pick it up yet, so should. So let's start right away. By the way, I should mention that Alex, by now, today he is in Trento, but as of the end of October he will be at Witwatersrand. So that's my outline. I tell you about why we are doing this, yes, I should mention that I'm a hard-boiled physicist, so if you, I'm not about, not the person who is really rigorous, but rather what it's good for. Not quite. Okay, so that's my outline. We'll talk about some aperiodic heterostructures. Then the main part, which will be about the Morse and paper folding structures. And then I'll speculate about things that really interest us and why we are really doing all this. So one part of the motivation is if you want to get a grant, okay? So there are applications. There really are applications. So there are quasi-regular heterostructures, which are quasi-one-dimensional layered structures. Then they are very popular in microelectronics. Then there are 2- and 3-dimensional things that are more interesting. Those are photonic and phononic metamaterials. So if nature didn't prepare for us crazy enough structures where we are dealing with, you can do it, and they even can be used, for instance, as of optical and acoustical bandpassfilters. If you want to make them as isotropic as you can, then aperiodic structures are very useful. And then how you can do it, in the electronics labs and the industry, the most popular things is a combination of gallium arsenide, aluminum gallium arsenide. In the lab slang, it's called GaAs-AlGaAs. But you can also play with other 3, 5, or 2, 6 semiconductors. You can do it with also with germanium silicon. And recently, what's very popular is porous silicon. You can you have silicon, and you can modulate its porosity, and by that you can really, on the same material, you can create more materials, and that has the advantage, the big advantage, that you don't have to have spacers. So and of course, one way, and we've got really an expert here, Ron. You just send waves through a material and modulated by wave, by an acoustic wave or an optical wave. So that's just to give you an idea how these things look, about the heterostructure. So that's a little piece of it. They are very popular in electronics. Originally it's done because the two materials have different bandwidths, but you can play with the composition. That's quite interesting. And just to get an idea, the machine that normally does it is MBE. That's molecular beam epitaxy. So what's look at this. That's no, never mind. So it's really a vacuum chamber, and you have little furnaces, fusion cells, where you will put your material, and you can close them and open them, and the whole thing is in high vacuum, and it's also cold. And then you have here a mass spectrometer, and this thing that's RHEED stands for reflection, high electron diffraction. So during the process in situ, you control and monitor the process, and the whole thing, as you can see, is in a clean room. You see that the guy who works on it wears a fancy dress. So so that's here I stop talking about technology and industry, and what we are really interested in, we're just that's sheer intellectual curiosity, and we are really interested in the properties of multidimensional substitution systems. About the one dimension is we know quite a lot already. Not everything, but quite a lot. And then we worry about fundamental questions about determinism, order, disorder, complexity, entropy. And I must say, we started out very naively and thought that this is quite well known and well understood. And we went up against the wall. I think we know, or I can only repeat Socrates to say, Enida, I know one thing, I don't know anything. Okay, so I'll tell you now what we are really doing. Now, on the one side, we started out with constructing double-sided versions of the standard substitution sequences. That's the well-known Fibonacci, prior to a Morse paper folding, period doubling, Golay-Rudin-Shapiro. And as you can see, the spectral properties, the spectral properties are well known, and the complexities are well known and calculated, but that's not true for higher dimensions. Here I should say a few words about credits. As you can see, there are more names than you are used to. Now, you all know that these sequences were discovered discovered and rediscovered many times in vastly different contexts. And so just recently I learned from Roger Penrose that Fibonacci, old Fibonacci, had a predecessor in India, and probably in India it was at least 100 years ago, earlier than Fibonacci, and perhaps it was in principle known many centuries before that. The person who really went after producing a sequence which was cube-free, no 3 consecutive A's, for instance. That was Axel Tour in the beginning of the 20th century. A few decades later, Morse in America rediscovered the sequence while he was dealing with differential equations, and it turns out that 50 years before Tour, Prouet already found the sequence. The same is true for Rudin Shapiro. Rudin and Shapiro, they are both in America. Rudin, by the way, was just a graduate student, and they discovered it independently. But it turns out that Golay, who was a communication engineer from the Swiss Romande, but mostly worked in the United States, discovered the sequence even earlier and even in a more general context. He worked in optics, and he mainly tried to simulate noise in transmission lines. And so there are so-called Golay sequences. So probably there will be more names, okay? What we are doing, these two people, Barbe and student von Heseler, they produce algorithms for for generalizing these sequences to higher dimensions. I must say, if you try to read this paper, it is rather indigestible, and they really unnecessarily complicate things. So we got the general idea from them, but made it much more simpler and easier. Okay, so that's what we are doing in principle. So I'll show you how this works, and I remind you to those who are in Kyoto that I talked only about the PTN, that's to a Morse. Now we added the paper folding, and we are trying to do more. Okay, so in one dimension, this is well known. The recursion these are the recursions. You just read them. Normally, if you look into a textbook or into the Sloan's encyclopedia, you'll find the recursions for the one-sided sequences, and mostly, but you have to be careful. Mostly it suffices to expand rather than in say in powers of 2, in powers of -2. Okay, that's the easy way to do it, but you must be careful that it really, and take care that it really works. Okay, so these would be the recursions, and that's the way we work. We work with a generalization of this recursion. As you can imagine, that say when you expand the natural number or the integers in powers of -2, then for instance +2 you have to represent as 4 - 2, and therefore you jump around, and I'll come back to that. Okay. So to start, this works in any dimension you want. Okay. So for a start, we just stay in 2 dimensions, and I've got an X to grind there. We participate in an experiment, and if time permits, and you ask me, I'll tell you a word or 2 about the experiment as well. So the generalization is, rather than expanding in -2, in powers of -2, we expand in, we use a matrix M, and as you can see, this doesn't work too well, but you can see that the structure of the recursion is more or less the same. Okay, and for a start, just what you need, it must be an expanding matrix. Okay, you can't expand in a unimodular matrix, and so the simplest thing you can imagine is this matrix. So this is the PTM case. So after iterations, you just calculate, and that's the results after certain iterations. It works like 2 or more. PTM it multiplies by powers of 2. So in this case we have here exactly 2 to the 13 points, and as you can just see, right, when you look at the picture, you can see that you have to look at a little bit more carefully. It's anorthotropic, that is, X is different from Y. It's chiral, as you can see. This thing is a kind of, or let's say, in that case it would be right-handed. And moreover, it has also a fractal boundary. The fractality is due to the algorithm. Okay, so that works quite well. And and I'll have later on a few words. I'll tell you about this. As you can. You might have guessed already the product will depend on the matrix. I just chose this special matrix, but can choose any other matrix, and it turns out that unlike in the one-dimensional case, depending on the matrix, you get all kinds of structures, among them even periodic ones. It suffices to take this matrix, which is simple enough, and you'll get, that's kind of a surprise. Root 2 and more is rather nasty. It's not even quasi-periodic. And its generalization may turn out to be periodic. So you have to keep that in mind. Okay, so that would be the periodic case. Again, it's again anorthotropic, and it's periodic. X is different from Y, but it's periodic, and again it has a fractal boundary. But that's the algorithm that does that. Now for the paper folding, again, I don't think you quite remember, but you can see that again the recursion is a generalization of the one-dimensional recursion, and we again took the same matrix. Okay. Now the result looks for instance like that. As you can see, well, there are more points here, but it's only after 9 iterations. We've got more iterations than 9. But if I had shown you the, say, 13 iterations, then to see anything, I would probably need a big screen. As you can see, the whole it's scattered all over the place. Okay. Now, perhaps right at this point, I'd mention that I was quite disturbed by this, quite irritated by this, and I thought, well, we have to find some more reasonable algorithm, and we are working on it. As a matter of fact, what I'm doing is something that's very obvious and very simple. Rather than fold your sheet of paper only in one dimension, you can do it in 2. And you can imagine to do it in n dimension as well. And that will work probably better. Okay, just to show you something, we can. That's a 3-dimensional example, so it also works in 3 dimensions. Now I come to what really the essence, why we are really doing it. Look, when you talk with physicists, chemists, material scientists, they speak very loosely about order and disorder. And mostly you understand, what is meant. But these things are really not defined. Okay? And it's something like hot and cold. Cold, hot weather, hot soup is different from hot electrons, and cold weather is different from cold atoms, and even cold weather is very different in Ouagadougou, Seoul, or Mekong. Okay, those are different things. So you have to exactly know what you are talking about. So about hot and cold, that's already quite settled. You can measure it with temperature, or if you want, okay, you can just use other units. You can use energy or frequency or wave number. That's equivalent. Now we'd like to quantify order and disorder, rather disorder. So somewhere in first grade or in kindergarten, I was taught that entropy is a measure of disorder. But it turned out that when you really think of it, it doesn't work too well. Okay. So again, instead of entropy, you can use Shannon's information, which is the same as negentropy. And so then you ask the question, is determinism the same thing as order? And we are really worrying. I am not promising to find definite answers. I'm speculating about this. So, in the first place, we found that entropy is insufficient to characterize such structures. You can look into more detail, and you can try to calculate or try to find the symbolic complexity. Let me remind that's the function of counting the number of words, the original definition of a certain length in a certain structure. The generalization is obvious. You take some pattern, say a rectangle or something like that, and you ask how many different rectangles you have in your given structures. So as you can see in, by the way, I copied this from Ferenczi, who was already mentioned here. For these one-dimensional sequences that's known, well, if it's periodic, it's trivial. All these, as you can see, they behave linearly. I didn't write that down, the PTN. It's a little bit more complicated, but in principle it's known. But then I bumped into something that I learned just recently, and that's the Champanon sequence. That's, to remind you what it is, you take all natural numbers and concatenate them. So you would write in 0, 1, 2, 3, and so on, and that's the Champanon number. In this case, you do it in the binary representation, so you start 0, 1, 1, 0, 1, 1, and so on. And this thing is perfectly deterministic. So for me, that's order, and it has complexity 2 to the n. And hence, by this formula of topological entropy, it has entropy log 2, exactly like Faber-Nurri. So clearly, this shows me that entropy doesn't tell me that this thing is stochastic. So let's get to what we've done. So we start after we have produced these patterns, we computed the symbolic complexity. We started with lattice animals, and we learned a few things, namely that as I showed you a while ago, you can see with your eyes that that pattern which I showed you in PTM was chiral, okay, and anisotropic. Now, when say so when I looked at a lattice animal of this kind, sometimes they also call them polyominoes. It turned out that some of them will appear in the right version, but not in the left. Only one enantiomer. So that really proves that this structure is chiral. Okay, even if you can see it, but you have to ask to prove it. Okay, so that was what we started out. We started to see whether we can calculate the symbolic complexity of the lattice animals. But that's a formidable job. So we learned something from the mathematicians that I'm very, very sorry that Valérie Berthet isn't here yet. That we can compromise on the rectangles, and so we did that. So we are doing it, but we wanted to get some results fast. So we limited the rectangles to lines, rows and columns. Okay? And this confirmed the chirality and orthotropy. The fractality comes from the algorithm. As I said, the algorithm jumps all the time and leaves empty holes which you have to fill in later at the later iteration. And the result was that for the two-dimensional PTN, the complexity is approximately quadratic. For the paper folding, it's approximately linear. So I'll show you the table if you and just look at the lowest entries, and you'll see that for PTN it is more or less quadratic, but perhaps a little bit it goes a little bit faster. Perhaps it's polynomial. Okay. In the paper folding case, it turns out that it looks like, I would be careful about that, it looks like that after some initializations, there's a formula that looks like 8 times n minus 2. And that's really suspicious because Alouche proved that in the one-dimensional case, after n equals 7, it's 4 times n. And that's a conjecture, and that has to be proven. And also we are trying hard really to get some formulas, which in this case is not so easy. And that leads me exactly to this thing, that while the recursion in one dimension gives us a very definite answer. In more dimensions, depending on the matrix, and you can have infinitely many matrices, so you get infinitely many structures. So, well, the matrices have integer entries, so it looks like a countable infinity, but can we find a canonical prototype of PTN? And then you don't want, when you have a structure like that, you'd like to have some characteristic figure of merit, some characteristic, some concise characteristic, and so entropy fails. And well, I speculated a little bit and looked what they are doing in deterministic chaos. And well, I found that in certain cases, but just in a very limited context, Steve Pincus suggested approximate entropy. it's again, I find it too complicated and not revealing enough. So the best I can for the time come up is perhaps to represent the symbolic complexity as a power law, and look at the exponent. Okay, so in that case, if that's really true what I showed you, so then a periodic sequence would have exponent 0. Those sequences have exponent 1, and this example of PTM would have exponent, say, 2 or 2 something, 2 plus something. And now really I think we have to think about fixing the notions. Is deterministic irregularity, by the way, that it's in a way equivalent to question, and there you have a paradox. Long ago, maybe 100 years ago, Borel invented the notion of a normal number, which in this case I showed you one. The Champernon number is a normal number. So that's a number where the digits are equally distributed. They are like in Bernoulli, but they are deterministic. And it is very hard. It turns out that Borel proved that the non-number numbers are of measure 0, so most numbers should be normal, but it's very hard to find one. And people don't even know whether pi or e or the square root of 2 is normal. And it turns out that the square root of 2 behaves better than the square root of 3 behaves better than the square root of 2. So these are questions which are which look very naive, very simple, and are very non-trivial. And so how can I tell the difference between deterministic irregularity and stochasticity and randomness? So I'll come to my conclusions. As I repeat, the complexity of 2D PTM is at most polynomial, hence the entropy is 0. The complexity of 2D paper folding is roughly linear, and it seems that it follows that formula after, I think, after 16 or so. It's 8 times n. Oh, sorry, that's n minus 2, not n minus 8. That's, before that it was the right thing, n minus 2. And again, hence the entropy vanishes. And what we are doing now is try other instances of PTM and PF, change the matrix, other structures, 2D, maybe 3D, and as I said, we are trying to do some better algorithms. The algorithm is very efficient, but as you can see, it scatters things all over the place, and introduces the fractality, which is not really essential. And then we try to find the characteristic. And find the formulae for these two complexities. So with that, I'll say thank you to all, and I think we can stop right here.